Hey, good morning, guys. Assalamu alaikum. Welcome back to Inspire Teens Grade 12 Physics/Chemistry, where in today's lesson, we are going to be continuing with, as you can see, chemical equilibrium. Okay, so let's just do a quick recap of what we've done so far so that we can continue. So we discussed chemical equilibrium. We said that chemical equilibrium is a dynamic chemical reaction, okay, which is a continuous series of forward and reverse reactions that are occurring constantly. That's what continuous means, right? Definition: a stage in a chemical reaction where the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, we also have certain reaction conditions. It has to take place in an isolated system, and it has to be a reversible reaction, meaning there has to be a forward and there has to be a reverse reaction. Okay, we discussed what is a forward and a reverse reaction. Okay, we discussed enthalpy, which is the heat of reaction, delta H. If it's less than zero, it's exothermic. If it's greater than zero, this is supposed to be all the way around. If it's greater than zero, then it should be endothermic. Okay, there we go. And the delta H given is always for the forward reaction, and the reverse reaction would be opposite to that of the forward. So whichever one is given, if it's given as exo, that means the forward is exo, and then the reverse would be opposite, which would be endo, right? Then we basically describe, we try to relate this chemical equilibrium or a reversible reaction in an isolated container. We just try to sort of relate it using diagrams. Okay, so yes, we discussed that the forward reaction converts reactants to products, and the reverse reaction converts products into reactants. Okay, and we had this little box where we had products and reactants, and we understand that when a reaction starts occurring, okay, initially, if we have to go to these graphs, right, initially we have a certain amount of reactants and we have zero product. We have a certain amount of reactants, but we have zero product, okay? And what happens is as this reaction starts occurring, you can see that we start using up our reactants, but we start forming products, okay? And that relates to the rate of each reaction. So the rate of the forward reaction starts off high because we have a lot of reactants, right? Remember, the forward reaction converts reactants to products. So the rate of the forward reaction starts off high. And initially we have the rate of the reverse reaction is zero because the rate of the reverse reaction doesn't occur initially because we have no products. But as the rate of the forward reaction, as we start forming reactants, the rate of the reverse increases, but we actually start using up a lot of our reactants, so the rate of the forward decreases until they meet at this point, which is actually equilibrium. And at equilibrium, the rate of the forward is equal to the rate of the reverse. Okay, so this is just an example of that, right? This is chemical equilibrium when the rates are equal. The rate at which we are creating products is the same rate at which we are using them up. The rate at which we are creating reactants is the same rate at which we are using them up. Okay, that's what we said is rate of reverse, rate of forward, as well as what is chemical equilibrium. Equilibrium, or understanding the definition better, a stage in a chemical reaction when the rate of the forward is equal to the rate of the reverse, and what that actually means. Okay, then we discussed when a reaction is favored. Okay, I think we were discussing Le Chatelier's principle, and we'll go through that more in detail today. Okay, so this is important. This first page is important for us to understand. Basically, chemical equilibrium, understanding in terms of concentration, time, rate versus time, the basics. Okay, understanding what is the forward reaction, what is the reverse reaction, isolated container, what do we mean by the rate of the forward being equal to the rate of the reverse, all of those things, those are important for us to understand thus far. Okay, and yes, we discussed that at T1 in both graphs. That indicates to us that chemical equilibrium has occurred. Right, Le Chatelier's principle. Okay, Le Chatelier's principle, it states that when equilibrium in a closed, okay, so we've established equilibrium. Now we're going to discuss disturbances to equilibrium, and that's why we're discussing Le Chatelier's principle. When equilibrium in a closed system is disturbed, the system will counteract the disturbance by favoring the reaction that opposes the disturbance. Now, this might not make perfect sense right now, so you may be able to memorize it, but you'll see once we actually discuss it, you'll understand what the reaction does when each type of disturbance occurs. Okay, so one more time, Le Chatelier's principle states that when equilibrium in a closed system, that's just equilibrium happens in a closed system, when it's disturbed, the system will counteract that disturbance by favoring the reaction that opposes the disturbance, basically to re-establish equilibrium. Okay, disturbances to equilibrium are of three: temperature, concentration, and pressure. Okay, these are considered disturbances. So when we increase, that's why this arrow is going up or down. When we increase or decrease temperature, that's a disturbance. When we increase or decrease concentration, that's a disturbance. When we increase or decrease pressure, that's also a disturbance. Okay, so equilibrium likes to chill. Okay, it doesn't want to be disturbed. It wants to remain in its state of equilibrium. Who wouldn't, right? So therefore, when you change in temperature, when there's an increase or decrease in any of these three, it is considered a disturbance, and the reaction and the system will always try to do something about that disturbance. Okay, it will always try to do something that sort of reverses that disturbance. Like if you want to increase temperature, the reaction is going to try and decrease temperature. It wants to go back to its equilibrium. Okay, so what happens when temperature is increased? The endothermic reaction is favored. Okay, and a quick thing to remember why the endothermic reaction is favored. So this endo favored is just like a shortcut of remembering it. Okay, remember when we increase temperature, why do we favor the endothermic? Because the endothermic reaction actually absorbs heat. So why is this important? Because it makes sense, right? If there's an increase in temperature, what does the system want to do? The system wants to decrease the temperature again. How do you decrease the temperature? By absorbing that heat. That's why the system favors the endothermic reaction in order to absorb that excess heat. Okay, let's look what happens when temperature decreases. When temperature decreases, the exothermic reaction is favored. Why? Remember, the exothermic reaction releases heat. Okay, the exothermic reaction releases heat. So when there's a sudden decrease, just say this reaction is chilling inside of its isolated container, everything is peaceful and at equilibrium, right? It was fine until the temperature decreased all of a sudden. Now, the system is upset. It doesn't want the temperature decrease. It wants to go back to its state of equilibrium. So because the temperature is decreased, it wants to now increase the temperature again. It wants to increase it back to what it was to counteract that disturbance that had occurred. So because when temperature decreases, the reason it favors the exothermic reaction is because the exothermic reaction would release heat. And since the exothermic reaction releases heat, it will counteract the temperature drop. So the temperature drops, but then the system favors the exothermic reaction. So it releases heat, so it brings the temperature back to what it wants. Okay, cool. So please, these are the only things, this is the specific reaction that is favored when temperature is increased or decreased, not anything else. It's not forward reaction is favored or reverse reaction is favored. This is what would be favored. If temperature is increased, the endothermic reaction would be favored. If temperature is decreased, the exothermic reaction is favored. So that's what you need to memorize. And then dealing with the specific question or the specific reaction, you can then determine which one is the exo or which one is the endo. Okay, and then you can say forward or reverse. Okay, now let's have a look at a change in concentration. Now, when there is a change in concentration, okay, firstly, there can only be a change in concentration of a gas or a substance which is aqueous, okay, so basically not a solid. Okay, not a solid. Okay, so the concentration, you can't change the concentration of a solid. You can change the concentration. So concentration is only relevant for gases and aqueous. Okay, so when it comes to concentration, it says here, when there is an increase in concentration, the other side is favored. Now, what does that mean? We're going to explain it here quickly. Let's draw up a reaction. We have A plus B gives us C plus 2D. Okay. Now, when we increase concentration, we can either increase the concentration of a reactant, or we can even increase the concentration of a product. Okay, but any of them could occur. We could increase the concentration of A or B, those would be reactants, or we can increase the concentration of C or 2D. And now that's where the difference occurs, in which one we increase. Are we increasing the concentration of a reactant, or are we increasing the concentration of a product? Let's just say we were increasing the concentration of A. Now remember, again, the system is not happy with any changes. Okay, the system is not happy with any changes. So when there's an increase in concentration in A, what the system is going to try and do, it's going to try and decrease the concentration of A. When the system has such a high concentration of A, it wants to decrease that high concentration of A. That's what it wants to do. It always wants to counteract. Okay, number one. So in order for it to decrease the concentration of A, it needs to use it up. So it basically needs to use up A as a reactant. And which reaction is that? That would be the forward reaction. Okay, because the forward reaction uses reactants as reactants, right? The forward reaction uses reactants to form products. So what happens when there's an increase in concentration? The other side is favored. So here we have reactants and here we have product. So when we increase the concentration of reactants, the other side is favored, the product side is favored. When we favor the products, we favor the forward. You guys need to remember this. This is where we're coming back to this. If you want to favor, so let's read this again. Forward favored means the products are favored or the products increase. Reverse favored means the reactants are favored or the reactants increase. The way I like to remember it is reverse reactants. If you want to favor the reactants, you shall favor the reverse. If you want to favor the reactants, you should favor the reverse. Reverse reactants, reverse reactants, reverse reactants. So of course, if you want to favor the products, you should favor the forward reaction. Because when you favor the forward reaction, what happens is that so favoring the forward reaction basically like promotes the forward reaction. It's like the system tells the forward reaction to occur more at a higher rate. Okay. So when you favor the forward reaction, what happens is that there's a decrease in reactants and an increase in products, because now you're favoring the forward reaction. The forward reaction takes reactants and creates products. The forward reaction takes reactants and creates products. So when you favor the forward, you are using up more reactants, so decreasing them to form more products, so increasing the products. Reverse reactant, so reverse favors reactants. So if you want to favor the reactant side, you should favor the reverse reactants. So the reverse reaction, sorry. So when the reverse is favored, basically the reverse reaction uses up products to form reactants. So when we favor the reverse reactant, the amount of products we have decrease and the amount of reactants that we form increase. Okay, so let's go back here. If I increase the concentration of a reactant, the other side is favored. Whenever you increase the concentration of anything, the other side is favored. So what does it mean by the other side? So because you increase the concentration of the reactant, the other side is favored. So the product side is favored. If you want to favor the product side, you will favor the forward reaction. So therefore, the forward reaction is favored. Okay, let's try a different example. What happens if I increase the concentration of B? Actually, the same thing, because I'm increasing the concentration of the reactant. The other side should be favored, so the forward would be favored. What happens if I increase the concentration of a product? The other side should be favored. Because you increase the concentration of the product, the reactant side needs to be favored. So you favor the side that favors reactant, reverse reactant. So the reverse will be favored. Okay, and that's basically how we determine what is the other side. So when there's an increase in concentration of anything, a reactant or product, the other side is favored. Okay, that's what we mean by the other side. If you want to favor reactants, remember, you need to favor the reverse. If you want to favor products, you need to favor the forward reaction. Okay, so that's for concentration increase. Now we can discuss concentration decrease. Okay, when there's a decrease in concentration, the same side is favored. So when there's a decrease in concentration, for example, we decrease the concentration of B. So we decrease the concentration of a reactant according to Le Chatelier's principle, by the way, because all of these, all of these are according to Le Chatelier's principle. Le Chatelier's principle states that these are the changes that will occur. This is what the system will do in order to counteract that disturbance. Okay, so when you decrease the concentration of something, the same side is favored. So you're decreasing the concentration of a reactant, the same side is favored. If you want to favor reactants, you favor reverse reactants. So the reverse is favored. Okay, let's do the other side. If you want to decrease the concentration of a product, okay, the same side is favored. So you need to favor the products. To favor the products, you favor the forward. Forward favored. Okay, I hope that makes sense. Okay, so if you're when you increase concentration, the other side is favored. When you decrease concentration, the same side is favored. Okay, putting it in simple terms. Let's have a look at this. When we talk about increase in pressure, okay, so when you increase pressure, the less mole side is favored. Now, when it comes to pressure, you should only consider the molar ratio of gases. You should only consider the molar ratio of gases and nothing else, okay, when it comes to pressure. So when there's an increase in pressure, the less mole side is favored. Now, to determine which side is the more mole side or the less mole side, okay, we can use this. So let us change this up a bit. Now, if we look at this example, we have 2 moles of A, which is a solid, added to 3 moles of B, which is a gas. Obviously, A, B, C, D, these are just arbitrary variables. They don't necessarily represent a specific chemical element. They don't at all. Okay, so those reactants form 2 moles of C, which is a gas, and 2 moles of D, which is also a gas. Now, if you want to this is for pressure and chemical equilibrium. If you want to determine the molar ratio, you might make the mistake and say, okay, the side with more moles. So how do you determine the amount of moles? You basically add the molar ratio. So this side has 2 plus 3, which is 5 moles. And then this side has 2 plus 2, which is 4 moles. So you might initially think that the left-hand side has more moles than the right, but you'd be wrong because you need to only consider gases. When it comes to chemical equilibrium, dealing with pressure, you need to only consider gases. So this is a gas, that's a gas, and that's a gas. You cannot consider the first one because the solid, we don't consider the solid. Okay, so this is basically a 3 mole ratio on this side, and here it's a 4 moles of gas. Okay, because we don't consider that. Sorry, that would have been 5 actually. I don't know. I should have put 5, but I think I did put 5. But anyway, we don't consider the solid. We consider the gas, has 3 moles, but there's 2 gases, so we add them, so it's 4. So the side with less moles in this case is this side here, the side with the reactants for the specific equation. So when you increase pressure, okay, I forgot to put here, how do you increase pressure? By a decrease in volume. By a decrease in volume. Okay, basically you compact something. If you're dealing with a closed container, you push the container closer and closer to make it smaller. That would be decreasing its volume and increase the pressure. Okay, so by a decrease, and a pressure increase by a decrease in volume, the less mole side is favored. The less mole side is favored. So in this case, the less mole side is the left-hand side, which is the reactants. If you want to favor the reactants, you favor the reverse. So therefore, the reverse reactant is favored. Reverse favored. Okay, let's have a look at a decrease in pressure. A decrease in pressure by an increase in volume. So how do you decrease pressure? Maybe you have a closed container and you expand it. You make it bigger. So you increase the volume, that would decrease the pressure. Okay, remember, only consider the moles, the molar ratios of gases. So when you decrease pressure by increasing volume, the more mole side is favored. So we've determined the moles here, and remember, only consider gases. Okay, only consider gases. So because the right-hand side has more moles, we would favor the right-hand side, which is the products. If you want to favor the products, you favor the forward. Favor the forward. Okay, that's for a decrease in pressure. Okay, and that's basically all of our concepts, all of the disturbances, the possible disturbances discussed, as well as the Le Chatelier's principle. So Le Chatelier's principle states all of these things. The Le Chatelier's principle states the changes that will occur. Okay, the opposing forces, or the opposition, or the opposing thing that the reaction does in order to counteract the disturbance or the stress. It's also known as the stress. Okay, so when we have an increase or decrease in temperature, when you have an increase or decrease in concentration, or when you have an increase or decrease in pressure, okay, these are considered stresses. The system was fine, it was at equilibrium, but then this disturbance came along, and what the system will try to always do is go back to its equilibrium by counteracting, doing the opposite to what the stress did. So here, remember, we increased temperature. Here it technically decreased because it absorbed all that extra temperature. Here we decreased temperature, it favored the exo, so that the exo could release heat to balance out the chemical reaction. Okay, then concentration. We said other side is favored when it increases, same side is favored when it decreases, less mole side when pressure increases, more mole side when pressure decreases. Okay, I hope that makes sense. So one note that I'm going to make here for all of them is just how they look on the graph and how the change occurs. So for temperature, you should always look out for a gradual change, because with temperature, the change is always gradual, and you'll see it will make more sense when we do our graphs. And for concentration, it's a rapid change in concentration. And for pressure, we also expect the rapidness, a rapid change in pressure. Okay, and it's important to understand that. You'll see why. It's important to understand mainly that temperature is gradual, while the other two are rapid changes. Okay, especially when looking at our graph. So that's our disturbances to equilibrium and what Le Chatelier's principle states in order to counteract them. Let's go ahead and discuss a catalyst and its role in chemical equilibrium. So a catalyst, firstly, a catalyst increases the rate of yield, but does not increase the yield itself. So basically, it's saying here that a catalyst, okay, increases the rate at which we produce our product, but does not increase the amount of product that we produce. That's what yield is. Okay, yield is the amount of product that we produce. Okay, so a catalyst, what it does, if you guys remember that from rate of reactions we discussed, right? The catalyst basically it decreases the amount of activation energy we need. Okay, it doesn't change the reactants initially. It doesn't change the amount of products we form. All it does, it takes us from reactants to products faster. That's all it does. It takes us from reactants to products faster. So it increases the rate at which we produce. It doesn't increase our production. Okay, that's what this means. A catalyst increases the rate of yield. Yield means how much we produce, but not the yield itself. So it doesn't actually increase how much we produce. Just increases the rate at which we produce it. Now, a catalyst is not considered a stress. A catalyst is not considered a stress. That's why it wasn't under the temperature, concentration, pressure. It's not categorized same. It's not considered a stress. So if you had to add a catalyst to a chemical reaction, it's not a stress. Equilibrium is not upset. It's perfectly happy with that. So now let us discuss, firstly, the concentration versus time graph. Okay, what the effect of a catalyst has on the concentration versus time graph. So here we can see this is perhaps the concentration of one of the reactants. Okay, one of the reactants. This is a reactant graph. This is a reactant graph. The concentration versus time graph for one of the reactants. Okay, and we can see that we start off with an initial amount of concentration and it decreases until it reaches a certain amount, and we can deduce from that at this time, whatever this time is, perhaps it's time T1, the reaction has stopped. Oh, actually, no, this is chemical equilibrium. So we understand that the reaction hasn't stopped, but the rate we've reached chemical equilibrium. That's all I should say, because we've been through the rest. But we can see that at T1, chemical equilibrium has been reached. Okay. So how would this same reactant, how would its graph look with a catalyst? With a catalyst, essentially what would happen is we would reach the same amount that we would reach previously at equilibrium. Okay, it would decrease to the same amount of reactant that it decreased to previously at equilibrium. However, okay, and we start off with the same amount, so we start off there as well. However, it will just reach that amount in a shorter amount of time. So we have a graph that looks something like this. Okay, it's not a perfect looking diagram. But what happens here is, maybe it's not such a drastic increase, but it doesn't really matter. Let's call this T2. And this is the concentration versus time graph with a catalyst. Okay, and what we can observe from this graph is essentially that we start off with the same amount of reactant. At equilibrium, we have the same amount of reactant. It's just that a catalyst takes less time to get there. Okay, so let's just call this time 1 and T2. Please, time 1 and time 2 doesn't mean 1 and 2 seconds. It's just the first time interval and the second time interval. So the first time interval would definitely be faster. T1 is definitely lower than T2. So a catalyst basically reaches equilibrium faster. So what happens to the rate of reaction? Okay, the rate graph. So as you can see, we have a rate graph. And we have the forward and the reverse reactions, right? Remember, we explained how those work. And we can see that here we have equilibrium. Okay. So what happens now once the system is in equilibrium? Okay. Okay. Yeah, so basically, yeah, this catalyst reaches that same equilibrium, just quicker. Okay. So we at equilibrium. Okay. So what happens now? We at equilibrium and we add a catalyst. If we at equilibrium and we add a catalyst, what happens is to the rate, okay, both reaction rates go up. Let's try and put them very close, but not completely touching. Both reaction rates go up, okay, and they reestablish equilibrium. Let's separate it a little bit just so that you guys can see that both reaction rates are going up. Okay, so both reaction rates go up. Sorry, 1 second. Okay, so both reaction rates go up and reestablish equilibrium. Okay, that's how a catalyst would affect equilibrium. Okay, it's not considered a stress. Okay, it's not like temperature, concentration, or pressure. Okay, it's not considered a stress. It just increases both reaction rates and reestablish equilibrium. So at T2, what happens is a catalyst was added. Okay, and equilibrium was reestablished essentially. Okay, so that's what happens at T2. So catalyst not considered a stress. Okay, simply increases both rates and reestablishes equilibrium. A concentration versus time graph when we add a catalyst. Okay, cool. Okay, please, if you guys nobody asked you. Okay, please, if you guys have any questions, don't be scared to ask, and rather ask when we're doing it, so that if you're confused about something, before I move on, I can explain it to you. Okay, so make sure to do that. Those on YouTube, for some reason the chat is not working. I'm sorry about that. I'm going to try and sort it out. I'm not sure. It happens for some live streams, but yeah. Okay. If you have any questions, you're free to join the Zoom and ask the question there or WhatsApp me or something if I see that. But yeah, okay, cool. Let's continue. Right. So that's what a catalyst is. Now let's just discuss one more thing about pressure. So remember when we discuss pressure and we ask like which side is favored, we need to know which reaction is favored. Okay. Whenever it comes to any disturbance, the question that comes after we have a disturbance is which reaction would be favored to counteract that disturbance or to counteract that stress. Right. So when it comes to pressure, we have to look for the moles, right? We have to look for the moles of gas on either side. Okay. And when we have to look for the moles on either side, so therefore, okay, and then when there's an increase in pressure, we look for the less mole side favored. When there's a decrease in pressure, we look for the more mole side. Okay, and then we'd favor that side. What happens if there's no side with less or more? What happens if there's an equal amount? So let's just say we have 2A solid plus 3B gas gives us C gas plus 2D gas. Okay, now if you consider the gas's molar ratio, you can see this is 3 and this is 1 plus 2, which is 3. So here it's equal. So what happens when we have the molar ratio on either side of the equation, either side of the chemical reaction for the gases equal, this is what happens. If the molar ratio of gases are equal, pressure increase would have the same effect as a catalyst, and it is not considered a stress. Okay, pressure increase would have the same effect as a catalyst, and it is not considered as a stress. This is when if the molar ratio of the gases are equal on either end. Okay, pressure increase would have the same effect as a catalyst. So it would have this effect, and it is not considered a stress. Okay, so that's the last thing that we need to discuss about the Chitalius principle and the disturbances, respective disturbances to chemical equilibrium. Now we're going to talk about graphs, which are really important. So I need you guys to pay attention. Right? Let's try and get through all of these concentration versus time graphs. Okay, sorry, yeah, all of these concentration versus time graphs. Okay, so we'll be referring back to these because we'll need them, right? This is something that you need to memorize, okay? When there's an increase or decrease in temperature, increase or decrease in concentration, or increase or decrease in pressure, okay? So we'll be working, please note, for all of these equations, sorry, for all of these graphs, we'll be working with this equation, which is Haber process, not really important, but we'll be working with this equation. So all of the graphs in this note, in these notes, are relevant to this equation. Of course, you can like different graphs would, I mean, different equations would work differently, but the concept you're going to learn from one single equation. Okay, so all of the graphs, even the pressure versus, even the rate versus time graphs, are based on this equation, and the forward reaction, sorry, the forward reaction for this equation is exothermic. Okay, because delta H is greater than 0, so therefore the forward reaction is exothermic. So yeah, this tells us that the forward is exothermic. I'm just going to write exo. And if the forward is exo, because delta H is less than 0, and then the one given is always for the forward. And if the forward is exo, then the reverse is opposite. So the reverse is endothermic. The reverse is endothermic. Forward exo, reverse endo. Okay, that's for all of these graphs that we're going to discuss. Now, the first one that we're going to discuss actually is a temperature change, and it's an increase in temperature. Now, we're going to discuss how it affects these graphs, concentration versus time. Now, for all of these graphs, we have the same template, as you'll see. It's the template that we've learned so far. So some of graphs that you might see maybe in a question paper, they might only start here, and that's fine. Okay, if they like start here, that's perfectly fine. Okay, because you don't have to consider this part. Remember, I told you this part is the part that represents us reaching equilibrium. Okay, a disturbance to equilibrium is what we focus on in chemical equilibrium. The disturbance to equilibrium, not the disturbance that happens anywhere here. So remember, we start off with a certain amount of reactants, and we start off with no products eventually until we form a certain amount of products, until what happens, chemical equilibrium is established. So we need to understand here at all the T1s, chemical equilibrium is established, right? And I'm going to write it only for the first one. chemical equilibrium is established. Okay. And yes, like I said, don't be confused if you see a graph that starts here, because some graphs would just start at equilibrium because that's what is relevant. Okay. Okay, cool. So yes, this is just the reaction occurring. This is where chemical equilibrium is occurred. And at T2, at all of the T2s is where the disturbance is occurring. So at T2, this is where the temperature is increasing. This is where the disturbance is occurring at T2. So after equilibrium is established, at T2, what happens is there was an increase in temperature. Now, we have to go here and we have to look at TCP, which obviously by the time of the exam, whenever you're writing a test, you need to have all of this in your head. You need to memorize which reactions are favored. Okay, so temperature TCP. So when temperature increases, endo is favored. Not forward, not reverse. The general thing is that endo is favored. That's what we should memorize. So now we know that endo is favored. We need to determine which one is endo. Since the reverse is endo, we can therefore understand that therefore the reverse will be favored. So temperature increase favors endo. Endo is reverse. How do we know endo is reverse? Because firstly, this tells us that forward is exo. Then we know that reverse will be opposite. So reverse is exo. How do we know that endo is favored? Because when there's increase in temperature, endo is always favored. And therefore, endo is reverse. So the reverse reaction is favored. Now, the reverse reaction is favored. We're going to see how that affects our graph from T2 to T1. So remember, reverse being favored. This is what it looks like. You're going to expect a decrease in products and an increase in reactants. You're going to expect a decrease in products and an increase in reactants because the reverse reaction is favored. So my product graph must look like that. My reactant graph must look like that. So reverse reaction is favored. What happens to my reactants? Reactants increase. Okay, both reactants increase. But the products decrease. Okay, now you'll see that this here, right, we curve it. These are curved. They curve, meaning actually what it actually means is there is a gradual change to the concentration of H2, N2, and NH3. Okay, and this is the gradual change that we were talking about when we discussed TCP. Right, we don't have to go all the way back there. But remember here we said that this was gradual. Okay, what gradual change were we talking about? And you'll see how it differs when we talk about concentration and pressure, because remember we said concentration is rapid and pressure is also rapid. Okay, and we'll see how the two differ. Okay, so this curve is actually representing a gradual change. Okay, so this is where, firstly, let's we're only going to do this for the first one. This is where, what color can we use? Let's use green. Okay, this is where equilibrium is. During this year, equilibrium is being experienced. Equilibrium. Okay, and that's from T1 to T2. From T2 to T3 is where Le Chatelier's principle is in action. LCP, okay, and technically like TCP, the temperature, concentration, or pressure, but that's where LCP is in action, because what's happening from T2 to T3 is the counteracting, the opposing of the change, of the disturbance, of the stress that was made. That is what's happening. Okay, so for this one, it's gradual. Okay, and from T2 to T3, and it's the same for all graphs, all concentration versus time graphs, that's where Le Chatelier's principle is in full effect. That's where Le Chatelier's principle tells us that the system counteracts. So from T2 to T3, it is showing us that it's counteracting to what? To then re-establish equilibrium. Because that's what happens at T3. Okay, so let's move this down a bit. I don't think we can do that. Never mind. At T3, what happens? Chemical equilibrium is re-established. So after, so let's go through the chain of events one more time. Reaction is occurring. Reactants are being used to form products. Products are forming until when? Until the rate at which the rate of the forward is equal to the rate of the reverse. That's what happens at T1. Chemical equilibrium. So at T1, chemical equilibrium is established. Boom, we have equilibrium. From T1 to T2, everything is nice and dandy. The system is very happy, the reaction is very happy because it's at equilibrium. From T1 to T2, everything is fine, everything is peaceful, there is equilibrium. What happens at T2? Very bad. Temperature increases. The system does not like this. This is a disturbance, this is a stress to the system. So what the system tries to do at T1, there is a change, like I said, there's a disturbance. Let's write here. Disturbance / stress. The disturbance or the stress occurs at T2. And what is that disturbance? There's an increase in temperature. So according to LCP, whenever there is a disturbance to a system in equilibrium in an isolated container, basically whenever there's a disturbance to equilibrium, Le Chatelier's principle states that the system will do anything, will do what it needs to. I'm just saying it in formal language. It'll do what it needs to counteract that change. So that's where our understanding of the TCP comes in. When there's an increase in temperature, the endothermic reaction is favored. We need to understand that the endothermic reaction is the reverse reaction. So because the reverse is endo and the endothermic reaction is favored, that means that the reverse reaction, of course, is favored. Now, the reverse reaction we can represent here. Firstly, it needs to be a gradual change because of temperature. Temperature results in a gradual change. Now because temperature results in a gradual change, we can see this gradual change showing the reverse reaction being favored. How do we know the reverse reaction is being favored? Remember, the reverse favors the reactants. So we see an increase in reactants and a decrease in products. So that is important and that is key, because sometimes you'll be given the graph and you'll be asked to answer questions, and you need to understand from this which reaction is favored. You need to understand from this which reaction is favored, whether it's the forward or reverse. And here we can clearly see the reverse is favored because the reactants increase and the products decrease. So that is the first concentration versus time graph for an increase in temperature. Let's have a look at a decrease in temperature. So when there's a decrease in temperature, again, all the same story. Reaction is occurring. T1, chemical equilibrium is established. T2 is where the stress is going to happen. What stress is that? It's going to be a stress of a decrease in temperature. Temperature is going to decrease. That's where we turn to TCP. What happens when temperature decreases? The exothermic reaction is favored. Which one is the exo? The forward reaction is the exothermic reaction. So if the exo needs to be favored, then the forward is favored, When the forward is favored, we will see what? When the forward is favored, we will see us using up our reactants. So the reactants decrease gradually. Reactants decrease and products increase. Gradual, And this gradual change is because there's a change in temperature. All changes to temperature occur gradually. So gradual change because of temperature. Here we need to be able to understand that these changes occur. We need to understand that we can see that the products increase, reactants decrease. That means that we used up reactants to form products. That must mean that the forward reaction had to have been favored. So that's how we draw this graph when there's a decrease in temperature. Let's look at an increase in concentration. More specifically for this one, we're going to deal with an increase in concentration of a reactant. And that reactant is N2. nitrogen. It's part of the reaction that we're working with. So there's an increase in concentration of what? Of N2 gas. Now, N2 is a reactant. We are increasing the concentration of a reactant. Let's go to TCP. See what happens when we increase a concentration. When we increase concentration, the other side is favored. The other side. So what do we mean by the other side? Because we increase the concentration of a reactant, the product side would be favored. In order to favor the products, you favor the forward reaction. So that's how we can conclude that when we increase the concentration of N2, we favor the forward reaction. So in order to favor the forward reaction, right, I want to favor the forward reaction. Remember that little diagram? Let's do this. Let's steal it so we don't have to keep coming back. Okay. Right. So remember, we said, okay, why are we favoring the forward? Because we're favoring the other side. We increase the concentration of a reactant. Whenever you increase the concentration of anything, you favor the other side. In this case, the other side for us is the product side. If you want to favor the products, you favor the forward. Okay. And this is how it looks when you favor the forward. Okay. You have a decrease in reactants and an increase in products. So that's what we're going to show on our graph. Favor the forward, you have a decrease in reactants. Okay, there's one thing I forgot. So I was about to draw them all like this, but that's not true. That's incorrect because it's not like constant. It's not like temperature. There's no gradual. There is a gradual change, okay, but there's also a rapid change. Okay, and we have to look out for this rapid change. So the rapid change would basically be the concentration of the reactant that was increased. Okay, so what happens is, because it's an isolated system, okay, we actually dealing with, because it's an isolated system, we're dealing like you inject more N2 in it all of a sudden. So there's suddenly a massive increase, not a massive increase, but there's suddenly an increase in the concentration of N2. So that we have to display on the concentration versus time graph. So what happens is only N2 will rapidly increase. I don't think my lines are perfectly straight. That's why, but it's fine. Okay, only N2 will rapidly increase. So that's something important that we need to see. Let's see if I can do this. Just make it a bit bigger. Okay, there is a rapid increase in N2 because we injected more N2, increase N2's concentration. Okay, thereafter, what do we do now? We follow the rule of which reaction is favored. So the forward reaction is favored. So we will then see a decrease in the concentration of the reactants, H2 and N2. They will decrease in concentration, and we will see an increase in the concentration of the products, which is NH3. Okay, and of course, equilibrium will be reestablished, right? At all the T3s, equilibrium is reestablished. Please keep that in mind. Okay, so there we see that rapid increase in the concentration of N2. Then, how do we determine from T2 to T3 the shape of the graph? Depending on which reaction was favored. Okay, so in this case, let's revise. Why was the forward reaction favored? We increased the concentration of the product or of a reactant, which meant the other side needed to be favored. The other side was increase this concentration. The other side is the product side. When we increase, if we want to favor the product, we have to favor the forward. Therefore, the forward is favored, and that's why our graph looks like this. When the forward is favored, we have a decrease in the reactants and an increase in the products. Okay, let's do the last graph, and then we can end it there. Okay, I know it's slightly over, but just bear with me. And then if you guys have any questions in the end, I'll stay for like a few minutes so that you guys are free to ask any questions. If you'd like to as well, you can unmute your mic And you can raise your hand actually, and I'll ask you to unmute your mic. And if you want to ask your question verbally, you are free to, and you can do that, or you can type your question in the chat or whatever it is. If something's confusing you, if you want me to re-explain something, or if you want to go through something again, whatever. Okay, let's look at this. Again, we are dealing with a decrease in concentration, and it's going to be a decrease in concentration of N2, the same thing. Okay, it's going to be a decrease in concentration of that same reactant. Okay, so when we decrease concentration, we turn to TCP. It says that the same side should be favored. The same side should be favored. So when we decrease concentration of N2, the same side, meaning the reactant side, needs to be favored. So you have to favor, if you want to favor reactants, you have to favor reverse. So therefore, the reverse reactant is favored this time. Remember, it is a gradual. There's no T3 here for some reason. Okay, it is a gradual change. Let's make our own T3, I guess. Okay, it is a, sorry, there's a rapid change. So what happens is you actually have, it's thrown in already, but you have a rapid decrease, as you can see here, a rapid decrease in the concentration of N2, because that's what happened. We decrease the concentration of N2, and then we follow the rule of which reaction is favored. Okay, so we already concluded that which reaction is favored. We said that the reverse reaction should be favored because we have to favor the same side that we decrease the concentration of. Okay, so we will favor the reverse. So when you favor the reverse, it increases the concentration of the reactants. Okay, it's going to increase the concentration of H2 and N2 from here at the bottom, because remember, it has to first rapidly decrease its concentration, and it would decrease the concentration of the product. Okay, and of course, at T3, they reestablish equilibrium. Okay, cool. So I hope that makes sense, right? These graphs, they can get a bit intense. Maybe the concentration versus time ones are not so bad. They get a bit more confusing when it comes to pressure versus time, but we shall cover it, and hopefully it's going to make sense. Okay. So yes, we have discussed the 4: temperature change, concentration change, increase in temperature, decrease in temperature, increase in concentration, decrease in concentration as well. Okay, so please, if you guys have any questions, I'll be here for the next few minutes to answer any of your questions. If you don't have any questions, and if you don't want to wait, you are free to leave, and I'll see you guys next week, where we'll continue with chemical equilibrium. Okay. No problem. You're welcome. Okay, there doesn't appear to be any questions. So thank you guys so much for joining. I hope that you guys have a good week and a good rest of your holiday. I will see you guys next week. Okay. Thank you. Jazakallah khair. Assalamu alaikum and goodbye.